Okay, so good morning and welcome. So this is course with the title Beyond NP Completeness. This is for IIT Jodhpur, but essentially I'll be doing parameterized complexity.
No, sir. No, sir. No. Sir, can you able to hear us?
Yeah, so we meet Monday, Wednesday, 11:30 to 1. So to justify this title for Jodhpur, I am not even going to define parameterized complexity today, at least. We'll get to that tomorrow. Today it will be something else. What is it? Okay. So first, what does it mean by beyond NP completeness? So what do you mean by, or what is the consequence of a problem pi is NP complete? What is the consequence? Some decision problem, let's say, pick your favorite graph problem. What do we know about? I mean, what do we mean by that, or what is sort of the consequence? What do we mean by that? There is a polynomial time reduction from some NP complete problem to this. That's sort of the formal definition, and it is an NP. But what is the consequence of it? What do we expect?
Research has been gone into solving.
No. So what do we know about pi? What do you believe about pi?
Does not help. It may not help on.
Yeah. So what we expect is that it is unlikely. And there is no theorem that it does not have. Yeah, so it is unlikely that I'm going to write this. The most general instance of pi has an algorithm running in time polynomial in the input size in the worst case. Right? There is no, you don't expect a polynomial time algorithm that will give you the correct. Let me also add.
Okay. I will call him back. Sir, அங்க விட்டு விட்டு கேக்குது அப்படின்னா கொஞ்ச நேரம் டெஸ்ட் பண்ணோம் அப்போ கண்டினியூ வந்துச்சு.
So what do you do?
Just I make a call to Ravi sir and ask.
Okay, you are recording it here, right?
Yeah.
Okay, so yeah, okay, check. I'll continue on the next one. So let me also modify it here as an exact algorithm. This is what we expect. Once a problem is NP complete, we don't expect for the most general instance of pi, but for every such instance, you have an algorithm which stops in time polynomial and input size and gives you the exact answer to your decision question. Or if I'm interested in some optimization problem, which is typically an NP hard problem, then it gives you this optimum solution in the worst case. So now, what are we talking about in beyond NP complete is, can we relax all this? And so, for example, what about special instances? Okay, so instances that have some structure, and maybe I don't need exact, but something approximate. If you are talking about a decision problem, approximate doesn't make sense because the answer is yes or no. What is the approximation to yes or no? Right? On the other hand, if it is an optimization problem, then you may not, you may be willing to relax, saying I don't want the optimum solution, something close to the optimum, and maybe in the worst case, maybe on average, okay, and then polynomial in the input size, but some good exponential. Okay, I have to live with exponential time, but what that means is better than brute force. So these are all these angles in which this beyond NP completeness have been studied. Right? So, so you look at if some problem is NP hard in some general graph, if I make some assumption on the structure of the graph, can you get a polynomial time algorithm? Can I get an approximation algorithm? It is a general graph, but maybe something I want approximation. Okay, it doesn't have a polynomial time algorithm, but does it have a sub-exponential algorithm? Instead of 2 power n, maybe there is a 2 power square root of n kind of an algorithm, or instead of 2 power n, I may have a 1.1 power n. Okay, and maybe I'm willing to trade, introduce some randomness in the input, and I'm happy with the good expected runtime. So all these are the angles when I said, or when we want to look at beyond NP completeness. Okay. Now, where does parameterized complexity come in? I would put it here, special instances, except we are going to parameterize what is special. Okay, and so somehow make the running time of the algorithm depend on that kind of a parameter. As the parameter is small, I want an efficient algorithm. As it increases, I want something better. Okay, but we'll do a formal definition and do this later. So for now, I'm just going to look at this special case and say, for example, there are lots of these hard problems in general graphs. I want to look at trees. That's the really most simple structured graphs. What can we solve efficiently in trees? Right? So, okay, let's take some really trivial problem. Click. You want to find a subset of vertices which are mutually adjacent to each other, and one is interested in a maximum click in a general graph, and is there a click of size at least k is NP complete. But what about on trees? Can you solve click problem on trees? No? Click size is at most 2. So you just give us 2. So let me also add, forests. That's also a related class where every connected component is a tree. So I want to find clicks in a forest. Shall I simply say 2 as the answer again? Very good. So if you have a component of size at least 2, then you know a click size is true if every component is of size. So it's absolutely trivial, right? You just have to scan the graph, look at the sizes of these components. Let's take this complement problem, which is the max independent set. Okay, again it's a maximization problem. In the standard reduction between click and independent set is take the complement of the graph. A click here would correspond to an independent set, and so if you solve this, you can solve this, vice versa. Does the same thing work on trees? Yeah, the complement may not. Most likely, it's not a tree. Right? It's a dense graph. So that doesn't work. You can't just say, okay, take the complement, solve the click problem. Okay, so how do I find maximum independent set in a graph, in a tree? It's already somewhat non-trivial. It's not as trivial as this. Okay, let me add more things here. Vertex cover. I assume you know all these parameters. If not, just sort of look up. So vertex cover, dominating set, so one purpose of my lecture is also to introduce these parameters and talk about different kinds of algorithms for these problems on trees, and then I will end with lead you with some simple generalization, and I want you to think about whether they are solvable in polynomial time. Right? So feedback vertex set. Okay, so let me write what these are, right? So this is pairs IJNS. An independent set would be exactly this, except it's okay. What is the vertex cover? It's a set of vertices such that for all IJV, I or J is in S. Dominating set is for all V in V minus S, where X is in U in S, such that UV is in E. Okay, and feedback vertex set is a set of vertices such that for all cycles C in G, S intersection C is not. Right? If you think of the vertex set of C. These are all some of the famous NP-hard problems in general graphs. Let's see, is there anything which is completely trivial like click on trees or forests? Right? Everybody see that? Feedback vertex, there is no cycle at all in the tree, so has a feedback vertex of size 0. Right? So this is also completely trivial. Okay, we'll spend some time actually designing algorithms for these problems. Okay, so what's it? Are they listening? Are they hearing?
Yeah.
There. How do you say it? Okay, good. Okay, so let's start with vertex cover problem. So we have a graph or a tree here, and you want a subset of vertices such that every edge is covered by this set. That means that if you pick any edge, either both endpoints or at least one endpoint should be in S. So essentially the remaining thing is independent. And now we are told that it is a tree and we want to design an efficient algorithm for this problem. Okay. So what is a tree? Just quick sanity check. Connected acyclic graph. Okay. So this whole thing works even for us because you can just apply it on every connected component. Okay. So so one easy observation is that every tree has a leaf vertex. So let's look at a leaf vertex, right? So suppose this is a leaf vertex, right? And remember that a vertex cover should cover every edge. So that means that if you have an edge, at least one endpoint must be there in the set you are trying to pick. So what can you observe about a leaf vertex? So this edge has to be covered. So X or Y should be picked in the solution. And you are better off picking Y rather than X, right? So without loss of generality, pick Y in S. So what do I mean by this? Let me actually, all of you would have seen this, but you may not have seen what I'm going to do, which is a formal proof of this, right? So what I mean by this is that if X is of degree 1, the size of the optimum vertex cover of G, right? Size of min vertex. So I hope it was clear that it's a minimization problem, because if you are talking about maximum vertex cover, you can pick the entire vertex and it will cover all edges. So it's a minimization problem. Size of minimum vertex cover of G is equal to 1 plus this is the K. So X is of degree 1, Y is its unique neighbor. Let's try and prove this. Because if we prove this, then we have an algorithm which gets started, because we find the leaf vertex, find its neighbor, include it into the solution, and then basically delete it, find the minimum vertex cover of the remaining graph and add 1 and you get the minimum vertex cover of the graph. So it's sort of a recursive graph, a recursive algorithm. You can just prove it and implement it fairly efficiently. Okay, so why is this true? Let's give actual formal proof. I haven't even thought through, but let's see whether I succeed. Okay, so you have some equality. So one obvious way to show it is to show that this is less than or equal to that, and this is greater than or equal to that. Okay, so which is easy. So what is being claimed is that you have a vertex X, this is Y, this is the remaining graph. Oh no, actually I delete Y also. Then I pick the remaining graph. This is G minus Y. So what does G minus Y means? That you delete Y, delete all edges incident on Y, and actually X will be sitting here. Okay, but that doesn't matter. Find the minimum vertex cover here. Yeah, actually let me put X also here. So you're going to delete y and all edges incident on it. So x would be a vertex in this graph. Find the minimum vertex cover plus 1 is the minimum vertex cover of the whole graph. So which direction is easy, or is that the only way, or some other way you want to show? Whatever. Let's see.
You just showed that opt VC of G is less than or equal.
Okay, I did not show anything. I just hand-waved something. So you're saying that this is less than or equal to 1 plus opt VC of G minus y. Why? So how do you do this? So you find the minimum vertex cover here, right? Realized by that number optimum VC of G minus y. And then add y to it, and the claim is that that will cover all edges. Why? Because the edges are of the two type, the edges are entirely inside, then the opt VC of G minus y will cover that. Or the edges are incident like this, then y would cover that. So I have produced you a vertex cover for the original graph from the minimum vertex cover of G minus y. So this plus this is the opt vertex cover of the whole graph. Okay, so this is easy, right? So find, okay, you don't even need to find, I don't even need to do an algorithm. Let S be min VZ of G minus y. S union y is a vertex cover of G. So the optimum vertex cover, I produced you one, so optimum vertex cover size would be at most this. Okay. How do you show it's greater than or equal to?
So in a vertex cover of G.
Okay, so let so converse, right? Or I want to show the greater than or equal to. So I take a vertex cover. Okay.
You will either have X or Y.
It will definitely have X or Y because we need to cover this edge. Okay. So S prime X or Y is in S prime.
Because G minus XY is G minus XY, you can get rid of that vertex and get a vertex cover.
But if it contains X,
You can still, you are actually getting rid of XY, not just Y.
yeah, you are actually getting rid of X. So the entire remaining graph is going to, if it contains X, you have a bit of a hard work to do. Because it is not exactly this.
No, I'm saying the second graph is G minus XY.
When you're getting rid of y, then it's G minus x. When you're getting rid of x, it's
No.
G minus x.
X is isolated vertex. Get rid of y. You don't need to cover x.
So what do I do? First thing I will do is, why should S prime contain X? There is no reason for S prime to contain X. So let me create another minimum vertex cover which does not contain X, right? So let's call it S double prime be S prime minus X. Instead you put Y. First of all, it will continue to be a vertex cover because you removed X, the only thing it might have lost, in fact, if Y was already there, then it's all, now you wouldn't have lost anything. The only thing you have lost is you did not cover this edge, so I'm going to put Y. So, every other edge is covered. And cardinal to S double prime is less than or equal to cardinal to S prime because maybe Y was already there. If Y was already there, you just remove X, that's all. So it actually has come down. So, but since this is the minimum vertex cover, this will also be, it cannot be strictly less, so it's equal. Right? Sorry, not a let's say minimum vertex cover. Okay, good. So now I have a vertex cover which contains y. Good.
What I'm trying to say is g minus y might as well have been g minus xy. So you got rid of both those vertices.
Because it's an isolated vertex. Okay, I mean, okay.
Then you can.
Okay, so we're still not done. Let's see. So what have I've just told you now that, hey, I have a minimum vertex cover which contains y. Good. So now, what do I have to show? What do I have to show now? To show that this is less than or equal to this, I have to now.
That minus 1.
Okay, so what do I have to show?
So if you just say that.
So what do I need to show? I need to show that opt of g minus y is less than or equal to
Of g minus.
opt of vc of g minus 1, because that's what I mean, I have already shown less than or equal to. I really want to show greater than or equal to now, which means that this is less than or equal to this minus 1. So now I have to produce you a vertex cover for g minus y, whose size is this. If I produce you a vertex cover of g minus y, whose size is this, I'm done. So what is that vertex cover?
Just remove one of those vertices.
There is no one of those, if you follow the steps. What is it?
You remove y.
You remove y, right? There is no x. So now the claim is S double prime minus y is a vertex cover of g minus 1. If I show this, then you know that I produced you a vertex cover of g minus y. So opt, if any, would be less than or equal to whatever the size of this, which is this minus 1. Right? So why is this a vertex cover of g minus y? So what I have is a vertex cover of g, which was my S double prime, which contained y. Now I have removed y. So it's, this is my S double prime. I just removed y and I have the remaining graph. And I claim that for this remaining graph, whatever I had minus y is a vertex cover.
In that graph, you don't have any edges that are incident on y.
Let's just show it carefully formally. How do I show that something is a vertex cover?
Every edge must be incident on some vertex.
Yeah, let's follow that definition. So you pick any edge here. I want to show that one vertex of S double prime minus y is sitting there. Why? Because this edge was there in the original graph as well, and S double prime was covering it. Y cannot be covering that vertex, this edge. So there must be somebody in S double prime minus y that's covering it. Okay. So my whole purpose of doing this is not that some brilliant idea which you did not know, but it requires this carefully steps to argue this. Okay. Right. So pick any edge uv of g of S double prime. Since none of this is y, so u or v must be in S double prime minus y, as S double prime was a vertex cover of G. So in particular, S double prime must be covering this edge. You can't use the help of y because neither of this is y. So there must be something here that should cover this. Okay, good. So now is it clear that from this lemma, so now you have actually proved this, that you have now at least a polynomial time algorithm, if not a linear time algorithm. Why? So what do you do? What property of trees are we using here? Every tree has at least one leaf, maybe actually two leaves. So you take a leaf, go to its neighbor, pick it into the solution, delete it from the graph, go find another leaf, because what you have is another forest. It may not necessarily be a leaf, but you have a forest. So every connected component, so you just pick a leaf, continue, keep doing this, until maybe you're left with all isolated vertices. That's great. No more edges to cover, and what you got is a vertex cover. Okay, so now the running time of the algorithm is just about finding leaves in your trees, and I'll leave you as an exercise to just see how carefully you can implement this. You can fairly in linear time you can implement this. Okay, good. So that concludes that you can find minimum vertex cover on trees fairly efficiently. Let's talk about dominating set. So what is a dominating set again? So for example, here B and E dominate every. So if you want to think of vertex cover as covering edges, dominating set is covering vertices. Vertices covering vertices, right? So B covers all its neighbors, so A, B, C. E covers these neighbors F and G. So that's a dominating set. You can see that that's not a vertex cover. Right, because this edge is not covered. Yeah, that's the only edge which is not covered. And I can have lots of vertices here with edges which are not covered, though even though you would dominate those vertices. So a dominating set is not necessarily a vertex cover, but is a vertex cover a dominating set? I needed that lemma. Okay, fine. So, yes, no, no.
Because in a disconnected graph,
okay.
you have an isolated vertex which does not need to be in the vertex cover, and that is not dominated by.
Okay, so if you have an isolated vertex in the graph, you don't, that may not be in the vertex cover, but dominating set you need to include it. So what about the graph? If the graph has no isolated vertex?
Then it is.
Okay, so no, if G has isolated vertices, okay, yes, otherwise, okay, I'm not endorsing it yet, but
yes,
you are claiming, yes, okay. How do you prove this?
If there is no isolated vertex, every vertex has an edge going out of it. That edge is covered by a vertex in the vertex cover.
Right. So if this is my vertex cover, then this is independent. Right. This is important. Useful property which will keep coming again. That the complement of a vertex cover is an independent set. So I want to show that this is a dominating set, which means that for every vertex not in the dominating set, I should find a neighbor. If you find a vertex not in the dominating set, since there are no isolated vertices, it has an edge. The edge cannot be here because this is independent. So the edge has to be here, and that guy would be a neighbor. Yep. Good. But since a dominating set need not be a vertex cover, the minimum dominating set size could be much smaller. For example, in this graph, BE is a minimum dominating set, but if you want a vertex cover you need to pick one from here, one from here, one from here, and so on. Okay, so let's again look at this problem of finding a minimum dominating set in a tree. Let's try the same idea of a leaf vertex. Right? Again, so suppose X is a leaf, and you have a neighbor Y. By the same token, I mean, there's no reason to pick X in the dominating set, because X is dominating itself and Y. Instead, if I pick Y, it will dominate Y and X and maybe even more. So the minimum dominating set looks like you're better off picking Y than X. Right? So X is a leaf, Y is its unique neighbor. Y could also be a leaf, by the way. Okay, so all our arguments will still go through. So is this true then if I want to talk about optimum dominating set of G is equal to 1 plus more or less the idea we used for vertex cover is that, if you have an edge x1, x is a leaf, there is a vertex cover, minimum vertex cover that contains y. The same thing is true here as well. So does it then follow that I can do the same thing, just pick y into my solution, delete y, move on? Yes, no? Maybe?
Probably not.
Probably not. Okay. Why not? I mean, either give me a counterexample or give me an argument why you think it may not be true. Some intuition. I mean, I don't need a formal argument. We'll get to that. Okay, I mean, let's take this example, what I've drawn here. Okay? Let's just take this example. What is the minimum dominating set if I delete y?
Yeah.
4, right? Because there are 4 isolated vertices. If I delete y, I have these 4 isolated vertices, you need to dominate them all each, so you need to pick it into the solution. So G minus y is 4, but for G it is just 1. So clearly it is not true. At least isolated vertices are killing you. But is it just isolated vertices, or? And why is this happening, or what is the? Okay, so maybe I should not just delete y. I should also delete all vertices dominated by y. Maybe that's an idea. I think at least that works here. Because y is dominating all these vertices, so why do you want to keep them? Just delete y as well as all the vertices dominated by y. Then for the remaining graph it's 0 and 1, so that seems to work. So with that,
If Y's children have other children.
if Y's children have other children, okay, good. So if it is like this, okay, suppose this is a tree, right? So Z is a leaf. So I'm going to follow this heuristic and say, okay, pick Y into the solution. And I'm going to say delete Y and all the vertices dominated by. So this is all dominated by Y. So I delete them all. Now I have to pick, these become isolated and I have to pick all of these vertices. Instead, I'm better off just picking Y and A2. Okay. So what is happening? Why did it work in vertex cover and what is the problem here? Ideas, yeah.
I take a subgraph, the dominating set restricted to that vertex cover restricted to that subgraph remains the vertex cover of this. And that's not the case with the dominating induced.
If you take a subgraph, the vertex cover with respect to that thing remains a vertex cover
Of that subgraph.
You are saying a tautology. You're saying you take a subgraph, look at the vertex cover. Oh no.
Fix the
vertex cover of the whole graph, project it to this subgraph. It is a vertex cover of this graph. Correct. Okay, good. So what he's saying is this, right? So here is my G, and I pick some subset S. In G, I have a vertex cover, and I say, okay, take that vertex cover. Let's say this is the vertex cover intersection S. So this is the vertex cover of G, intersection S. Now this set covers all edges inside. Okay? But that may not be true for dominating set because somebody outside can dominate the vertices here in a better way than trying to force a dominating set inside. Okay, that's one argument, sure. Another argument I might say, and that's what will lead us to a good algorithm, is the following: that if I delete, suppose I pick Y into the dominating set, and suppose I delete just Y, and I have the remaining graph, right? Just delete only Y. The vertices here are not of the same type as what we started off with. Right? There is now two classes of vertices. If I suppose I use the heuristic because if X is a leaf, I'm better off picking my neighbor. Then I pick that vertex into the solution, delete it because it has dominated itself and all its neighbors. Now in the remaining graph, there are two classes of vertices. What are the two classes of vertices? Vertices which have already been dominated. So you don't bother dominating them. But why do you want to still keep them? Because they may be useful to dominate others. Okay, there are sort of two kinds of vertices. You need to somehow differentiate it in your new graph, and then you apply some recursion and all that might work. If you just keep in mind that here are some vertices which I don't need to dominate, here are vertices I need to dominate. Which was not the case in vertex cover because that vertex has done the job and deleted, then any edge incident on that has already been covered, and the remaining graph you better cover all the edges incident on. Okay, so this idea that if you have a leaf you pick its neighbor is still correct, but to convert it into an inductive algorithm, you need to differentiate the two kinds of vertices, and then if you do some careful thing, it will work. Okay. So that's one approach to do. But I'm going to just now tell you some sort of a dynamic programming essentially captures it, and maybe again you have all seen that. So first I will do is I will root the tree. Okay, so now I pick some vertex x and my tree is rooted like this. Okay. So now I want to sort of do some dynamic programming, which means I'm going to build solutions bottom up. So let's see what sort of, if I have, what kind of whenever I'm going to talk about dynamic programming, the first thing you should ask me is, what are the sub-problems we're going to solve, right? This is the first question on dynamic programming. I'm going to apply dynamic programming, what are the sub-problems, sub-questions we're going to solve, right? And to answer that, let's start at the root and say, what do I need when I get to the root? What kind of information I need on the subtrees if I want to just solve the problem for this tree from something I have captured for these subtrees. This graph has several subtrees. Suppose I have computed some information for each of these subtrees and I want to pull out the solution for the entire tree from whatever I have computed for this information. So what kind of subproblems I want to compute? So and that depends on what kind of states you want to associate with x. So I'm looking for a minimum dominating set. Suppose x is in the solution. The solution is the min, or basically the dominating set. Okay, so x has these subtrees, x is the root. If x is in the solution, I don't know this, but I'm going to try all possibilities, which is the two cases, whether x is in the solution or x is not in the solution. If x is in the solution, then what kind of information do I want for the subtrees? That will determine what subproblems I need to compute, right? So what do I need? Optimum dominating set for each of the subtrees?
Minus the root.
Minus the root. You are welcome to use the root to dominate others, but you don't need to dominate. That is the information, right? So let's say I have T1, T2, T3, TL. Then the optimum, I'm going to say S means that x is in the solution, right? Optimum for the subtree rooted at x with x in the solution is equal to so let's say Tx, and I need to x to dominate x, okay? 1 plus, because x I have included it. I'll explain what this notation means, so it should naturally okay. Summation opt Ti where the root need not be dominated. Okay, so all I'm saying is, okay, so let's write this notation, which tells you what kind of subproblems I need to compute. So let me explain these notations. So opt y Tx x means the size of a minimum dominating set for Tx including x x is in the solution. And size of okay, I'm just making up these notations. Hopefully it's natural enough. So what I mean is, look at the subtree Tx including x. I want to dominate that, and I am forcing x in the solution. That's what this means. And opt of Tx means that I'm not forcing anything. You pick x or not, I don't care, but dominate including x. This says you don't need to dominate x. I'm not forcing it. Let's say this thing means I'm forcing something. If not, I'm not forcing anything. So now, with these notation, this should be clear, right? So the way we actually proved opt of vertex cover is equal to 1 plus this, you can actually prove this with a greater than or equal to, less than or equal to. So all I'm saying is, you want to dominate this and I want to include x, then find the minimum dominating set in T1, you don't need to dominate this. Find the minimum dominating set in T2, you don't need to dominate this, and so on and so forth. Add them all, and that's plus 1 because I'm including x. If you don't include x, then this is case 1. Then, okay, I can also add an wire. Specifically, I'll say dominate Tx union x, but exclude x. Okay, minimum dominating set that does this. Okay, so suppose I don't include x in the solution, then what is the size of the minimum dominating set? I can find the minimum dominating set of each of this and add them all. That's not quite enough, right? Why not?
It's possible you don't
Pick the root of any of these, and so x needs to be dominated. So that's the extra thing you need to worry about. So how do you want to dominate x? Just force one of the roots, right? And pick the minimum of which root you need to do. So that's it. So what do you want to do? So then I need that. So then opt Tx x. So I'm going to say no. That means x is not in the solution. Yes, I'm not picking anything, so I don't need 1. Minimum over 1 less than or equal to I less than or equal to L of what? Ti, no, opt y Ti whatever root plus summation j not equal to I okay, I'll let you pass the notation. So what am I saying? In Ti What is I? Well, run through all possible values. In Ti, I am going to force the root into my solution and say give me the minimum dominating set of Ti where I is forced, the root is forced. And for the others, no forcing, just find the minimum dominating set. Okay, I do want to dominate root because X refused to dominate it, so I dominate that as well, but I am not forcing anything. For every j, and add them all and run over all possible i's and pick this. Okay, this is also exactly one like we did. You can formally prove it. Okay, so the idea is that these subtrees, there are no edges across these, that it's okay to independently solve these problems with appropriate forcing and put them all together. And what is the opt of Txx? Pick the minimum of these two. Right? So you force y or do not force, whichever. So now this gives you an inductive way of solving the problem, because how do I know these guys? So to compute this, I need to know these. How do I know this? Well, just go bottom up, start from the leaves, and for the leaves, you can compute all these quantities at the leaves. Either you force them, include them, whatever, and compute these quantities, and then do a post-order traversal of the tree. So as you go up the tree, you have computed, when you reach a node, you have computed all these quantities for every subtree. And okay, so naively this algorithm would take how much time? How do you compute the running time of any dynamic programming algorithm? See how many quantities do you compute overall, and how much time does it take to compute one quantity, multiply them, right? So for every vertex, even if you compute all these four guys, so it will be like order n different quantities you are computing, and to compute one of them, here you are doing a sum, here you are doing a min of the sum. So it just naively, if you look at it, it looks like an n cubed algorithm, because this is like an n square step, right? Because this is a sum. So there is this big sum, and you are doing it some L times.
It's order n. I compute the whole sum on right hand side. I just swip two values.
Okay, good. So that is one way to do it. So that you compute this entire without the y. Correct. And then for an ith alone, you see whether opt y is bigger or smaller and adjust it. So is everyone following this? Okay, these are some details, how much time it takes. So I said n cubed because my rough crude analysis was that you are computing about order n things, there are n nodes, and each node you are computing some 3 or 4 things. And how much time does it take to compute a value from its children? If you look at this, for a particular I, it looks like some order n, and then for the L different, and which L could be order n, so it's like an n square. So Prateek's idea is that just compute the entire sum without the y, and then for every I you just subtract out something, and then do a min of that. So that's like an order n for each step. So overall looks like an n square. Okay, it's still not n square. Okay, why is that? Okay, so this is the, okay, so first crude analysis, n cubed, assuming that this is an n square step. Second, No, you can do this, compute this entire sum and subtract it for each I appropriately and pick the minimum. So it's like an order n, so it's like an n square. I claim that it's still not order n square, it's actually linear. Why? So,
We didn't access this quantity that often. So,
there's a cleaner, simpler argument than that.
You're doing a degree of
Exactly. For every vertex, how much time are you spending? Proportional to the degree of that vertex. Right? Because L being order n is like a too conservative estimate. Sum of the degrees of the vertex. Sum of the degrees. So what is it? Why is it order n?
At most 2n.
Yeah, because it's a tree. Sum of the degrees is twice the number of edges, but number of edges is because it's a tree. So overall, it's an order n algorithm. Right? Start from the leaves, go bottom up, and compute this. A clean order n algorithm to find the minimum dominating set size. It gives you its size, by the way. Doesn't it, how do you get the set? This gives you the size of the minimum dominating set finally, because that's what I've been, I'm adding this, and so these quantities are size. Again, the standard dynamic programming trick will actually get you the actual set. So what do? You just go and see what realize. So for every vertex, am I in or not, is something you store that information. As you just go up, whichever realizes the minimum, which tells you, what vertices are in, what vertices are not. So as you go up the tree. So for example, finally if you know that out of these two things, opt n is smaller, then you know that the root is not in the solution. Okay? And in fact it can go up and come down again. So suppose you realize that this opt n of this is smaller, then you know x is not in the solution. Okay, but x is not in the solution, who is going to dominate? Then we'll figure out which minimum realizes this. So that tells you that vertex is there. And when you compute this opt of tj, opt itself is minimum of opt y and opt n. Right? Because opt, how do I know? I am computing opt n and opt y, so whichever is smaller. So that will tell you whether that vertex is in or not. So finally you can go up and come down and get, mark all vertices in the dominating set. Okay, so at least for one example, work this out carefully and convince yourself that you can actually get the dominating set as well. So all this in linear time. Okay, so but required a little more work than just doing it for vertex cover. That was, by the way, you can do the same thing for vertex cover as well. Right? Write a dynamic programming like this, figure out whether x is in the vertex cover or not. If x is in the vertex cover, what do I need for each of these pieces? If x is not, what do I need for each of these pieces? And pretty much the same idea will work for doing a bottom-up post-order traversal to find the minimum vertex cover. So that's again another efficient linear time algorithm. Later on in the course, we will see that this can be generalized for what are called bounded tree width graphs. Right? So we will extend this notion of tree-like, define it, and towards the end of this course maybe. Okay, so we have designed an efficient polynomial time algorithm for vertex cover. Slightly different flavor. We got dominating set, and I said the same idea will also work for you with a different polynomial time algorithm for vertex cover. Click and FES are completely trivial. What about maximum independent set? On trees. Yep. Same idea will work actually. Okay, so I'll exercise, I'm going to say dynamic programming. No, this one let's go through it again. But is there a one-line algorithm for maximum independent set?
Root is included in the problem.
Okay, I'm going to do that. That is the dynamic programming, and that's not a one-line algorithm. What's a one-line algorithm for maximum independent set on trees? Having seen whatever we have seen. Find the minimum vertex cover. Whatever left is a maximum independent set. Okay, it's a nice, interesting, important property between vertex cover and independent set. Right? Find the minimum vertex cover. We know how to do it. We have seen two algorithms. I've seen one, and I told you another. Take the complement of that. That gives you maximum independent set. But let's see if I want to do this way. Then suppose X is in the solution. Then so now there is no such thing as dominate the root or not. So let's say X is in the solution, then what is it? So let's just define two terms. Opt of Y Tx, its max independent set size containing X, and opt no Tx means not containing X. So then what is this? So if X is in the solution, you are trying to find an independent set, a maximum size independent set. So what do I know then?
1 plus sum of max of no.
No, because I know that none of these vertices can be in my solution. So find the maximum independent set of this subtree with the extra condition that root is not in the solution. So whatever that thing is, right? So opt. So 1 plus summation opt no Ti. Right? So this is maximum independence. And suppose X is not in the solution. Should I just find the sum of the maximum?
So of Y and opt n.
Yeah, that would be. What is opt-n? I'm trying to figure out what is opt-n.
I mean, in the sum, you need to take opt Y and opt n, max of Y.
For each of them. Yeah, let's call that as opt. Right? So you find the maximum independence at here, 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 here. Add them all. Is that enough?
That should be enough, provided we are taking optimum. So again, we have the similar condition that none of the root might pop up in the optimum solution.
Correct.
The root of these subtrees would pop up in the optimal solution.
Okay.
But that case has been taken care when we included X into
Exactly. Good. Right. Yeah. So sum is enough. Okay. Now what I was thinking, yeah, exactly this point about. Suppose in this optimum, when you are computing these subtrees, none of the roots are in the solution. Then nothing that forces you to include X now and increase the size now. Whereas Pratik says that is already considered here, because that means that all of these opt ends are actually the opt, and that's actually considered here. It will show up here. Okay, so if X is not so case 2, if X is not in solution, then opt n Tx is that definition. That's equal to summation I equal to 1 to L. And no condition on the subtrace. You include the root or not, doesn't matter. And opt would be max of these two. So again, the same thing will work. You just start from bottom up, post order traversal, start from the leaves. Usually it's trivial for the leaves, and then you just, as you go up, so again you get an order n algorithm, because this time you spend on a node is proportional to the degree of that vertex. Okay. Okay, so we have seen this. What other problem is easy on trees, right? Let's add coloring, right? Chromatic numbering. You want to color the vertices of the graph such that whenever your adjacent vertices get different colors, and you want to use minimum number of colors. Okay, so what do you know about chromatic number of trees?
Just 2.
Yeah, tree, then 2 or 1 if it's a forest, could be 1. There are no edges. Otherwise 2. Why? Because
You need at least 2, and you need at most 2 because you can color the root one color and the children the other color.
yeah, so color the root and then color all its children another color, children another color, and so on. There won't be any conflict because there are no edges across levels or any problem. So this is another problem which you can solve in polynomial times. Okay, so now I'm going to just leave you with some little generalization, some exercises which we will pick up next week. So first thing is, let's look at bipartite graphs. Okay, what is a bipartite graph? It's what's a bipartite?
Can partition the vertex set such that there is no edges in the partition, but and all the edges will be exposed.
So there exists a partition of the vertex set into 2 parts such that there are no edges within each part. Edges are only across. Why is it a generalization of trees? Because trees are bipartite. What is the partition?
Root is a
Root, next level, start from the root, do whatever, the BFS, and pick alternate vertices at even level in one part and vertices at odd level in another part, and that's a bipartition. So bipartite graphs are more general than trees. So now you can ask all these questions in bipartite graphs. So this is what we mean by, the most general instance for the problem is hard, and we saw that very nice structured forests where all these problems are solvable in polynomial time. Let's keep expanding it, and what is the sort of the limit. So this is one approach to NP completeness. So we're saying bipartite graphs are natural generalization of trees. So which of the problems is trivial on bipartite graphs? Anything, maybe none of this is, that's also fine. But do you see anything, any of these parameters like we saw for trees? Do you see anything which is
Dominating set.
We see dominating set. Or you have to see.
sorry, what's it?
Equal size credited.
Click, max click. Max click is trivial. Why? Ashwin?
No triangles.
No triangles in the graph, because one of the characterizations of bipartite graphs is a graph is bipartite if and only if it has no odd cycle. Okay. If you have not seen this, please go verify this. There's a very simple, nice proof. So G is bipartite if and only if G has no odd cycles. Clearly, if you have an odd cycle, it is not bipartite, because if you have a triangle, then if I put it in part 1, this is in partition 2, I stuck. I don't know, I'm stuck, I don't know where I will put this. So odd cycles are sort of forbidden, but what this theorem or lemma says is that the converse is also true. That if there are no odd cycles, then you can actually partition it into 2 parts. Please go and verify a proof, work it out why the converse is also true. Okay, it requires a little bit of work, but not hard. Okay, so because there are no odd cycles, there are no triangles, so you cannot have any click of size greater than or equal to 3, right? Because if you have a larger click, there must be a triangle sitting inside. So the max click size is 1 or 2, which you go and trivially check. There is an edge in the graph, you got a click of size 2, exactly like for trees. So this is completely trivial. What else is trivial? Coloring, right? Because you can color it with 2 colors, because you have this 2 partitioning, and color this part with 1, color this part with 2, and edges are only across, so coloring is trivial. Anything else do you see? Okay, so here is an exercise. Show that these two are NP-hard. Okay, it should be very nice exercise, nothing hard, you just need to figure it out. And when you have not probably done some NP-hard reduction, these are some fairly simple exercises to show. So even if a graph is bipartite, dominating set is NP-hard, FES is NP-hard. Click is trivial. Between vertex cover and maximum independent set, you know that they have the same complexity, because if you find one, you find the other, right? The complement of that. And anybody knows? You've seen it, right? So this is vertex cover is polynomial time solvable, hence maximum independent set size is polynomial time, but it's not trivial like click. It requires some work. It requires some nice combinatorial theorems. Okay, what theorem? Yeah, this is Koenig's theorem, which tells you that the maximum matching in a graph, in a bipartite graph, is the same as the minimum vertex cover. Okay, so we could do that next time. I'll show that these two problems are polynomial time, and this is an exercise. So I really want you to try and come to me with solution before we start the next lecture on Wednesday. Okay. Let me give you one more generalization. That's another set of nice exercise. And that is, suppose I tell you that there are some k vertices. So it's tree, or let's say forest, plus k vertices. I give you this set. I tell you, here is a set of k vertices. You delete them, the graph becomes a forest. Okay? So the graph looks like some trees, collection of trees, plus some set S of k vertices, and my graph looks like this. You know, there can be edges here. I give you this set of k vertices as well. Now on this new graph, k is some okay, you can think of k as a constant, you can think of k as a parameter and analyze in both cases which of these problems are easy, hard. Just explore, think about it. Okay, so in the next class we'll start with vertex cover and bipartite graphs polynomial time using matching, and I will listen to the proofs of these NP-hard proofs from you guys, and then, you know, any thoughts on this problem. You know, if for example, if k is a parameter, if k is not constant, are these problems NP-hard? Are these polynomial time solvable? Or k is k? Then what kind of algorithms can you get? Okay, so that is the. So I want you to just think about all this. So today what we saw is on forest. I mean, we didn't really see all of them because these problems are completely trivial. We saw this dynamic programming algorithms. We will generalize this, as I said, towards the end of the class. One more exercise. Okay, so the other exercise is for vertex cover. We saw this algorithm. You know, delete y. Now, why does this completely solve the problem on trees? Because you can always find leaves. Every tree is a leaf, every forest is a leaf, so you can find a leaf, find its neighbor, include it, delete it. What you have is another forest, and keep doing it. But suppose the graph is not a forest, but it's a general graph. I can still apply this rule, because the correctness of this rule did not use the fact that it is a tree. Where did I use the fact that it's a tree? That there is a leaf, that's where. But if I find, in general graph, suppose I find a vertex with degree 1, I can always do this. Pick its neighbor, delete it, that correctness still follows, because we actually proved it formally, and nowhere I use the fact that it's a tree. Okay? This is true for any general graph. So suppose I do this, as long as possible, what happens? Suppose it's not a tree, it's a general graph, and I apply this. What happens? What will happen? What can you say about the resulting graph?
It's not a tree. No leaves. If it's not a vertex.
No leaves. There won't be any degree 1 vertices. Right? Yeah. So there won't be any degree 1 vertices. So if I keep, so the correctness did not assume the fact that it is a tree, so I can do this on any general graph. So if I keep applying this, as long as I find a degree 1 vertex, pick its neighbor, delete it, you know, and you got one vertex into your solution, you keep doing it. Finally you have a resulting graph which will have now no degree 1 vertex. Of course, if you have isolated vertices, that is also you can get rid of. So the minimum degree is 2, right? Now what I want you to think about is there a similar processing, one can do for degree 2 vertices. This is a polynomial time step. So degree 1 rule was if I have a neighbor, just pick the neighbor, delete it, was correct. You can prove that you can solve the optimum solution. Is there a similar pre-processing rule you can do to get rid of degree 2 vertices? But then why stop there? Can you do that? Is there a similar pre-processing rule for degree 3 vertices? Of course, this process cannot go on forever because yeah, so maybe then you've solved the whole thing. But that you don't expect because it's an NP-hard problem and all these steps are polynomial time. So somewhere this process has to stop. You can't, because this is an absolute correctness condition, right? It doesn't, you just say that, if you have a degree 1 vertex, pick its neighbor into the solution, delete it, work on the resulting graph. That's what we're saying. If you manage to find some sort of a similar sound rule for degree 2 vertices, then I can apply it and get a graph where there are no degree 0, 1 or 2 vertices. If I manage to find something similar for degree 3, I mean this process cannot go on because I'm just doing polynomial time, so eventually I would have solved the problem, which I don't expect in polynomial time. This is general graph. So this process should stop somewhere. Where? Where does it stop? Where does it stop? Okay, so that's the other exploration exercise. Okay, so we will continue on Wednesday then. Stop.